Hello and welcome back to question 5, differentiation. In this question, we have a sphere inscribed inside a cone. That means the outer surface of the sphere is touching the inner surface of the cone. And by touching, we really mean that it is a tangent to the sphere at the point of contact, which is a key piece of information we'll need later on. For the rest of the question, it is quite straightforward. In fact, do yourself a favor and just look at the diagram. Everything that's mentioned is reflected in the diagram. Part 1 wants us to show r square is equals to a square h over h minus 2a. Now, the initial reaction you might get is, hey, r square, hey look, there's a right triangle over here. If you consider the height of the cone, the base radius of the cone, and the slant height of the cone, I have a right triangle. R square plus h square is equals to slant height squared. Maybe I can make use of that. But upon inspection of the right hand side, you might realize that, hey, it doesn't really look like a square root of something square minus something square. So what else can we do? Remember the key piece of information. Now, when doing problem solving, you always have to pay attention to what is the key features, what are the special setups of this question, and that is the inscription of the sphere, which means if I were to draw a line from the center of the circle to where it glances the sphere, tangent to the sphere, we'll get a 90 degrees. We learned that in secondary school. And this line that I just drawn is the radius of the sphere, that's A. I'm going to call this part here L prime, simply because we usually use the cursive L to denote slant height, but this portion is only part of the slant height, so I'm going to call it L prime. And finally, the last side over here, right, so that I can have a right triangle. This height over here, or rather this dotted line, is h minus a. Yeah? Now, what is the purpose of drawing creating another triangle is that we have similar triangles. This triangle that I just created over here is similar to this triangle, right? How can we tell? First, they share an angle. They share one angle over here. Next, they share another angle, 90 degrees, which means the last angle of this triangle must be similar to this. Then I have a similar triangle to work with. Right. First, maybe I want to write L prime in terms of h and a using Pythagorean's theorem. Hypotenuse minus this side will give me the square of L prime. So that's my first working. L prime equals to square root of this minus this. Simplified, you get square root of h squared minus 2ah, which looks very similar to the denominator of what we want to show. So I think we're kind of on the right track. Now, the next thing is to use similar triangles and compare. I'm going to say that this side, L prime, corresponds to h, or the larger triangle. And I'm going to say that A corresponds to R of the larger triangle, which means L prime over h is equal to A over R by similar triangles. Right. And then I'm going to substitute in L prime and make R the subject of the formula. Move R to here, L prime to the bottom, move h to the sides, and I get R equals to AH over L prime. Now I'm going to square both sides. When I square both sides, I'm going to get this, R squared equals to this, and then I realize that I can divide by h for the numerator and denominator, and that leaves us with exactly what we're supposed to show. That is part 1. Now in part 2, we're supposed to show, using differentiation, the minimum volume of the cone, and proving it's a minimum, writing down the volume in terms of A. The first thing, of course, is to state down the volume of a cone, 1/3 pi r square height. And you realize very conveniently we just worked out r square. So let's substitute this inside, and this is what you get. Next, so we're going to treat A as a constant because we can write down in terms of A, and assume that maybe we can change the height. Yeah, and that means we're going to do dv dh. So dv dh is going to involve using quotient rule. Make sure that you do it slowly, meticulously, don't rush. Right, so this is where careless mistake comes from. And if you simplify, we're going to get something like in this form. Something in this form. You might get something similar to this. Okay, and I'm not going to bother doing any more simplification because the next thing I'm going to do is I want to show that, hey, for a minimum or maximum volume, dv dh has to be 0. So if I let dv dh go to 0, pi over 3 is never going to be 0. A squared will never be 0, and also the denominator doesn't really play a part in letting this thing go to 0. So either h is 0 or h minus 4a is 0. Now if h is 0, it doesn't make sense. It means we don't even have a cone. The height of the cone is 0, right? So we're going to reject that and say that, hey, h is equals to 4a. Right? And based on 4a, I need to show that when h is 4a, it is a minimum point. So the thing I'm going to do actually is not a second derivative test, but the first derivative gradient test. Why is that so? Taking a look at dVdh, if I want to do the second derivative test, it means I have to do the quotient rule again. And this is, I will have to expand it out first before differentiating, of course, which is additional work. Now compare that with the first derivative gradient test, right? When I do a gradient test and substitute h equals to 4a, maybe slightly less than 4a, 3.99a, or slightly more than 4a, 4.01a, what really matters is this thing in the brackets. Why do I say so? Because pi over 3 is positive, we know that's a constant. A squared h, if I substitute 3.99, 4, 4.01, it's always going to be positive here. Now the denominator is a square, so that is going to be positive all the way as well. So the only thing that can tell me whether dVdh is positive, negative, or 0 is just this term in the brackets. So when doing the first derivative test, we are as good as just looking at this bracket here. So let's look at my test over here. When I substitute, say, slightly less than 4a, say 3.99a, 3.99 minus 4a is going to be a negative, say, 0.01a. And because it's negative, the whole dVdh becomes negative, and I get a downward slope. For 4a, we know it's 0, so it's flat. Let's look at 4a plus. Say if I put 4.01 minus 4a, that will be a positive 0.01, and the whole thing is positive. I'm going to get a positive slope. This tells me that at 4a, it is actually a minimum point. Now the last thing to do is to state the volume in terms of a. So I've proven that v is minimum at h equals to 4a. So to find the volume, the minimum volume, I'm going to substitute 4a into this one. Yeah, that h equals to 4a over here, and you're going to get this. And when you simplify, this is the answer for question 5, part 2. Now I hope you found this useful, and I'll catch you in the next question.